In this video, we're going to go over matrix transformations, including linear transformations, like I have here, as well as rotation transformations, as well as geometric transformations. So let's first start off with these problems here. So find the image of this point that's given by the following transformations. What on earth is an image, and what the hell does this notation even mean? The image of a point is pretty much what are the coordinates of your transformed point. So after you've worked out the transformed point, after this has been transformed, you would get the coordinates of your image. So we know that xy has been transformed by this matrix, or by a set of rules to get these coordinates. So your x coordinates will become the x value plus the y value, whereas the y coordinates will be the x values minus the y values. So what we can think of is we can think of some coordinate xy being transformed by a matrix. So in this case, I'm going to say my transformation matrix is T. And after we have transformed them, we have gotten a new matrix. Okay, the coordinates of our new point is now going to be x plus y, x take y. So we need to work out what transformation will yield us with this matrix here. And the matrix that I know will work here is simply going to be 1, 1, 1, negative 1. So this is the matrix for T, and I'll tell you why. This is the matrix for T because if I was to multiply both of these matrices together, so if I multiply 1, 1 by xy, I get x plus y. And if I multiply 1, negative 1 by xy, I get x take y. So this matrix, right, this is the transformation that describes what the new xy values will turn into. Okay, so we know the xy values currently would turn into x plus y, x minus y like this. So in other words, we want to work out what is the image of the point 2, negative 4. So rather than just using any xy values, let's use the points 2, negative 4. So what is the matrix we get? What are the new coordinates that we get? So if we do 1, 1 with 2, negative 4, we get in the x value 2 take 4, which is minus 2. And in the y value, we get 1, negative 1 times 2, negative 4, which simply becomes 2 plus 4, which becomes 6. So this here, this 2, negative 6 here, is our image. Okay, that is the coordinates of the new point after the transformation has gone into effect. So let's have a look at part B now. Okay, so how can we work out what the linear transformation matrix is for this set of coordinate rules here? So we know what we can simply do is we can generate our transformation matrix, the linear transformation matrix, by just looking at the coefficients of x and y. So we know the x value, the first x value, has turned into 2x and 3y. So that means in the top row we get a 2 and a 3. And in the bottom row, we know the y coordinate has been transformed by the rule 4x plus 5y. So we get 4 and 5. Because now if we times this by any random coordinate xy, okay, the matrix multiplication of this is 2x plus 3y and 4x plus 5y. So it correctly describes that the coordinate xy is transformed into this rule here, as it shows in the question. But we don't really care about for xy, we care about for the specific coordinate in the question. So 2, negative 4. So let us now multiply these matrices out. So 2, 3 times by 2, negative 4, that gives us 4 minus 12. 4, 5 and 2, negative 4, that gives us 8 minus 20. So that is simply equal to minus 8 minus 12. So this here is our image. So this is the coordinate of the new point after the transformation. Now finally, let's look at the last one. So xy is transformed by this matrix here. So we know the matrix transformation has to be 11 minus 3, 3, negative 8, since those are the coefficients of the x and the y. And we're going to transform these. Okay, we're going to transform the coordinate 2, negative 4 by this matrix here. So let us now work out what the matrix transformation will be. It will be 11, negative 3, and 2, negative 4. So that'll be 22. That'll be 22 plus 12. And the y value, it'll be these two multiplied together. So it'll be 6 plus 24. Sorry, 6 plus 32. So these coordinates here okay, will simply equal to 34 and 38. So this is the coordinate of your image. That is the new point after the transformation. Okay, so this is the introduction of transformation matrices. Okay, this is our next problem here. Okay, we have the matrix. We need to find the matrix that has a linear transformation that will map 1, 0, and 0, 1 to these coordinates here respectively. Okay, and after doing that, we need to work out what is the image of our new point. So let us first work out what is the transformation matrix. Okay, so we know that the coordinate of 1, 0, okay, has turned into 3, 4. And we also know the coordinate of 0, 1 has turned into 5, 6. So we need to come up with a rule, okay, the same rule, that will map both of these points into our new images, which are these. So the way I'm going to do it is I'm just going to use a 2 by 2 matrix. Okay, rather than using two separate matrices for my coordinates, I'll just use one nice matrix. So my first point here is 1, 0. My second point is 0, 1. So 1, 0, 0, 1. Okay, so these are my 2 points. And these two, after they have been transformed, and your transformation is always pre-multiplied by the coordinates. Okay, so I'm going to write this down just to make sense. This is your coordinates. Okay, your coordinates are always pre-multiplied by the transformation. So now that you have this, we know that the new matrix coordinates, so 1, 0 becomes 3, 4. So that's your new coordinates. And then 0, 1 becomes 5, 6. Okay, so now let us work out what is the transformation matrix. Well, we know that this is simply the identity matrix, okay, so it doesn't make it all that difficult. Okay, the identity matrix here is simply the same as multiplying by 1. Okay, this is like the 1 in matrix form. So can't I just post-multiply both sides by the identity matrix? Well, yes, because this is really just cancelling out. So in this case, we get the transformation matrix. Transformation matrix is literally just 3, 5, 4, 6, like this. So now that we found the transformation matrix, this is our transformation matrix that will map these coordinates into our image. We need to find the image of the point 2, 3. Okay, so what we're going to do is we're going to take our transformation matrix and we're simply just going to post-multiply by the coordinates we want to transform. Okay, so we take the transformation and we multiply by the coordinates. And we'll end up with our image. And in this case, our image is just going to be the product of these two matrices. So 3, 5 times 2, 3, that will give us 6 plus 15. 4, 6 times 2, 3, that will give us 8 plus 18. And that will simply equal to 21, 26. And this is your image of the point 2, 3. Okay, now let's have a look at some geometric transformations. So our goal is to work out the matrix transformations for the following transformations. Okay, so what is the matrix T, which we can multiply by the coordinates to get our image? So we need to work out the matrices for each of these. And the way I'm going to do it is I'm simply going to describe how we can get a coordinate xy, okay, to be mapped into our new coordinates of our image. Okay, so we know that we have to make some x bar, y bar. That's our transformed xy coordinates. So here's how I'm going to do it. I'm going to take the identity matrix, okay, the identity matrix like this, and I'm simply just going to multiply it by coordinates x, y. If I pre-multiply any coordinates by the identity, I will return the original coordinates. Okay, so this has no transformation being applied to it. So how on earth will I get the identity matrix to describe a dilation of scale factor 2 parallel to the y-axis? Well, if it's a dilation parallel to the y-axis, okay, if it's parallel in this direction, that means I'm stretching out my y values upwards. Okay, that means my y values should become twice as long for the same x value. Okay, so I'm just going to do a little 2 here. And the only way I can get a 2y here is if I were to have a 2 in this matrix column here. Okay, so if I change this number to a 2 here, you can now see if I pre-multiply my xy coordinates with this matrix, I will end up with this matrix here. Okay, so this is the transformation that describes a dilation of scale factor 2 parallel to the y-axis. So now let's do the same technique with B. So I take the identity matrix. Okay, and I know some coordinates x, y are going to be transformed. Okay, so this will obviously return me x, y because we're pre-multiplying by the identity, which is just 1. Okay, but we know dilation scale factor 3 parallel to the x-axis. If it's parallel to the x-axis, that means all your x values are being elongated by a scale factor of 3. So the way I would write this down in my matrices is some coordinate xy will be transformed such that the x values will be 3 times as long. 3 times as long like this. So that means my transformation matrix will simply be a 3 over here, because now if I multiply these two matrices together, I will get 3x and a y. So that's how you can use the identity matrix to work out dilation matrices. Now let's talk about a shear of scale factor 3 parallel to the x-axis. And you might be asking, what is a shear? And to describe what a shear is, I'm going to draw a simple square. Okay, so a square would look like such. If I was to talk about a shear, okay, what that would mean is I would take my bars vertically like this, so the horizontal sides of the square like this, and they're simply being pushed in one direction like this. Okay, but they will still retain this shape here, should still have the same area as this shape here. Okay, so how you can think of it is think of it like these two sides are variable, so they can bend like this or they can bend like this. Okay, but you're just taking this corner here and you're pulling it this way. Okay, and if you pull it this way, you will end up with a shape like this. And this is a shear parallel to the x-axis. A shear parallel to the y-axis will look like this. Okay, so instead of these two being your fixed bars, it'll actually be these two that are your fixed bars. Okay, so it'll look like this. Okay, so think of pulling on this point, rather than pulling it this way and leading with this shape, you're pulling it upwards and getting this shape here. Okay, so that's what a shear is. So to describe the matrix of a shear, okay, all we can do is we can start off with our identity matrix. Okay, we can start with our identity matrix. And we can multiply some xy coordinates. So now that we have our identity matrix, okay, the shear will end up something like this. Okay, it'll end up as x and then plus cy. Okay, because that's what transformation you have in the x-axis. Your transformation is that little pull to the right. Okay, it'll be pulled to the right. And the way we can get this transformation like this is by simply replacing this 0 with a c here. Okay, so this matrix here describes the transformation or the shear parallel to the x-axis. And in this case, we know the shear is by scale factor 3. So we know it's 3 in the x-axis like that. So that means c must also be 3. So if we're doing a shear parallel to the y-axis by -1, rather than this number being -1, it'll be this number being -1. So it'll look like this. Okay, and this is a shear of scale factor -1 and parallel to the y-axis. Now let's have a look at the reflection in the x-axis. Okay, if we're describing a reflection in the x-axis, okay, that means that in our Cartesian plane, if we have a point like this, it will be transformed to a point over here. So we still retain the same x values, but now your y values have simply become negative. Okay, so if I look at my identity matrix, okay, we know the x values must retain the same, but the y value must be transformed to now -y. And the way I can generate this matrix is by simply making this number here -1. So this is my reflection matrix in the x-axis. And the last one is reflection in the line y equals to -x. So again, okay, let's draw a little Cartesian plane to visualize this. Okay, so if I have a plane like this, and I have the line y equals to x, negative x like this, what we can say is if I have a point over here, let's say this point here is 2, 3, the reflection across this axis should give me the point -3, 2, like this. This is -3, -2. So this is the point that's reflected across the line y equals -x. So what we're saying is we simply want to swap the x and y values, but then we also want to do negative of both of them. So both the coordinates become negative. And the way we can do that is we can start off with our identity matrix. Okay, and we know that this here will retain the x and y values. If we change the numbers 1, 1 to like, I don't know, 2, 2 or something, all that'll do is just dilate the x and y values. But we want to swap them. Okay, so rather than having 1 on the leading diagonals like this, we're going to have 1 on our lagging diagonal like this. So now what we get is 0, 1 times xy will give us y. And then 1, 0 times xy will give us x. So we've successfully swapped the x and y values like we wanted to, but we also want to make them negative. So the way we make them negative is by simply making it -1 in the transformation. So this is the matrix that will cause a reflection in the line y equals -x. Okay, and that's how you can work out what is the transformation matrix using the identity matrix. Okay, our next question is this one here. We're going to deal with rotation matrices. A rotation matrix is a matrix that looks in this form here. So it's cos theta minus sine theta, and cos theta. And this matrix will cause a rotation. It'll cause a rotation, I'll write it in red. Rotation anti-clockwise. Be very careful to say it is anti-clockwise only. Okay, by theta degrees. So in this case, we want to find the image of this point when it's rotated 90 degrees anti-clockwise. Okay, so what we want to first do, we'll answer it in a different color. So for answer A, rotation 90 degrees anti-clockwise, well, let's use the matrix. Okay, the transformation matrix is cosine 90 minus sine 90, sine 90, and cos 90. So if we evaluate this, what we get is we get 0, -1, 1, and 0. This will cause a rotation 90 degrees anti-clockwise. So now that we have this, okay, what we can say is let us now multiply our coordinates 2, 3 to work out the image. Okay, we can multiply by the coordinates 2, 3. And what we get is 0, -1 times 2, 3. That'll give us -3. And 1, 0 times 2, 3, that'll just give us 2. So this is the coordinate of our image. Okay, this is our image. Now let's do rotation 45 degrees clockwise. To do a rotation 45 degrees clockwise, okay, we'll do the same thing here, except instead of doing 45 degrees, okay, let's do -45 degrees, because that'll describe in the other direction of the x-axis. So you can do cos of -45 degrees, then minus sine -45, then sine 45 minus 45, and then cos of -45. Okay, and the values for this, if you have them memorized, is simply going to be root 2 over 2, and then minus of minus root 2 on 2, so root 2 on 2, then minus root 2 on 2, then root 2 on 2. Then what we can do is we can simply multiply this by the coordinates of 2, 3, because then that'll give us our image. Just to make life easy, I'm going to treat this as the matrix of 1, 1, -1, 1, and then factorize out a root 2 over 2 on the outside. I'm going to do this just to make my life easy. This is the same as root 2 over 2 times 1, 1, -1, 1 times by 2, 3. So let's first do the matrix multiplication. Okay, the matrix multiplication is 2 plus 3, which is 5, then minus 2 plus 3, which is 1. And we also have to remember the root 2 on 2 on the outside. So now if we wanted to simplify it out, what we would get is the new coordinates are 5 root 2 over 2 and root 2 over 2. So this is our image coordinate of the new point. And that's a rotation 45 degrees clockwise. Now the last one that we're going to do is the rotation 120 degrees anti-clockwise. So this number here, we can simply just make theta equal to 120. So what we can do is cos of 120 minus sine 120, then sine of 120, and then cos of 120. And if you don't know how to work out the exact values off by heart, I do have another video you can watch before you watch this one. So this one here, cos of 120 degrees is going to be minus a half, then minus root 3 over 2, root 3 over 2, and then minus a half. And again, I'm simply just going to factorize out a minus a half first. So what we can say is our transformation will be minus a half times by a 1, root 3, minus root 3, and a 1. Okay, and then we can times this by our coordinates we want to transform, which is 2, 3. So let us transform the coordinates of 2, 3 and work out the matrix. What we get is negative half on the outside. On the inside, we get 2 plus 3 root 3, and then minus 2 root 3 plus 3. Okay, I'm not going to expand out the minus a half, but you can notice this will be our image. Okay, this is our new coordinates for the image. Okay, and that's how you can use a rotation matrix to work out the image of an original point. Okay, is that next question? Another rotation matrix question. The point 1, 0 is rotated to point B 120 degrees anti-clockwise. So let us first work out the transformation matrix for this one here. Okay, so I'm going to call this matrix here, okay, this transformation T1, and point A is also rotated by point C by 240 degrees. I'm going to say this is T2. So let's first work out T1. Okay, so T1 is going to be, if it's anti-clockwise, what we can do is we can say it's cos 120 minus sine 120, and then sine 120, and then cos 120. That was the rotation matrix we just did in the previous question. And this is simply going to be, in this case, minus a half, minus a half, minus root 3 on 2, root 3 on 2, minus root, this is root 3 on 2, and then minus a half. So this is our transformation matrix for T1, and then T2, okay, we can do the same thing, but with 240 degrees. So cos 240 degrees minus sine 240, sine 240, and then cos 240. And this will simply equal to minus a half, then root 3 on 2, then minus root 3 on 2, then negative a half. So this is T1 and that's T2. Okay, and this is how you work out the matrix of the transformation. But what we need to work out is what are the coordinates of B and C. So let us now take both of these transformations and now work out what happens if we multiply them by the point 1, 0. Okay, so let's work this out. If we multiply the top matrix, I'll make it nicer. Okay, if we multiply this matrix by 1, 0, okay, what we get is this times 1, 0, so that'll just give us minus a half. And then this times 1, 0 is simply just going to give us root 3 on 2. So this is our coordinate of B. Okay, these are the coordinates of B. Then to work out the coordinates of C, we can do the exact same thing. Multiply this matrix by 1, 0. So what we get is minus a half and minus root 3 on 2. So this is the coordinate of C. Okay, so that's how we can work out using these two matrices here. What sort of triangle is ABC? Well, let us have a slight draw of this on our triangle on a Cartesian plane. So we have point A is going to be 1, 0. So I'm going to say 1, 0 is going to be roughly over here. That's point A. We know point B is going to be negative a half, so negative a half, and root 3 on 2, so it's going to be roughly over here. That's point B. And then we know that point C is going to be negative a half also, but then negative root 3 on 2. Okay, so now that we have it looking like this, we can recognize that this is a type of isosceles triangle. Okay, and the reason I can say it's an isosceles triangle, if I can draw properly, the reason it's an isosceles triangle is because we know these two lengths have to be the same because they are just equidistant from the x-axis. Okay, and these are our last two set of questions. We got one more after this. So we have two sets of transformations. We have a reflection first, then we have a dilation by a scale factor of 2. So let's find the matrix of our transformation if we transform by T1 and then by T2. And most people think that you would simply take T1, multiply it by T2, and that gives you the total transformation. However, you have to recognize if we multiply or transform a point xy, we would always pre-multiply by the matrix T1. Okay, that would give us the transformation of T1. Then, if we want to do the transformation of T2, we have to pre-multiply again by T2. So in this case, the matrix that gives us the transformation of T1 then T2 is actually equal to T2 times T1. Remember, because the order of transformation matters in this case, okay? Because we multiply by T1 first, or pre-multiply, then we pre-multiply by T2. So it's the same as doing pre-multiplication of T2 to T1. So let's work that out, okay? In this case, let's work out what the matrices are. A reflection in the x-axis, okay? So let's draw our identity. A reflection in our x-axis pretty much means that all the y values turn negative. So that means this number here must become negative. Okay, so we're doing T2 then T1 in our equation, but it's T1 then T2 in the actual transformation. Dilation of factor 2 parallel to the x-axis. If it's parallel to the x-axis, that means all the x values are getting enlarged by factor 2. So that would mean, if I draw my identity again, okay, all your x values will become twice as long. So this is what your new transformation equation will look like. Let us now multiply these two out. What you get is, if you multiply 2, 0 with 1, 0, you will get 2, 2, 0 with 0, negative 1, that'll give you 0, 0, 1 with 1, 0, that'll give you 0, and then 0, 1 with 0, negative 1, that'll give you negative 1. This is your transformed point. Okay, this is your transformation matrix. So now we do the same thing in part B, except this time we swap the order. We do T2 then T1. And let's check if the order actually matters in this case particularly. So if we do this one here, okay, we can just copy him. So rather than doing the dilation then the reflection in our equation, we do the other way around. We can multiply in this order here. Okay, so now let us work out the multiplication of these two. So what we get is 2, then 0, then 0, then negative 1. So in this case, the order actually doesn't matter, and it makes sense. Okay, if you were to take any point and actually apply these matrices yourself, not even matrices, apply these transformations yourself, you would notice that you would get the same point regardless of which order you did it in. So that's why the matrices you get are also happening to be the same. Okay, now let's have a look at this one. Okay, we're going to do the same thing, and we're going to work out what the matrices of T1 and T2 are. So to work out T1, okay, it's a rotation 90 degrees clockwise. So that means we can say cos of minus 90, because our normal matrix is anti-clockwise. So cos minus 90, sine minus 90, minus sine minus 90, then sine minus 90, then cos minus 90. So if we work this out, what we get is we get 0, then 1, negative 1, and then 0. So this is our T1. So now that we have T1, let's work out T2. T2 is simply equal to the reflection in the line y equals x. Okay, we did y equals minus x before, so let me show you how to do y equals x. So this is the line y equals x. Okay, if I draw it properly. Okay, so if I take a point over here, okay, if this point here is x comma y, then if we rotate it across the axis, sorry, we'll do it like this. Okay, if I then flip it across this axis here like this, what we end up with is x, y. We end up with y and then x. Okay, so if we then took a different point over here where the x value is negative, negative x, and the y value was negative, so negative y, the reflection here will simply become, or in this case it's actually y. What we would end up with is we would end up with y comma negative x. Okay, so in this case, the matrix we actually want to do is we want to swap around. So we can swap around our leading diagonal to get 0, 1, 1, 0. But then we just want to make sure that our, actually that's all it is. We don't care about the negative signs, nothing changed. We just swap the 1, 1 like this. So now let's work out what is T1 times T2, then T2 times T1. So for part A, if we're doing matrix T1 first and then T2, we would actually multiply it in the order of T2 first and then T1. Because remember, when we apply it to some coordinate xy, it's actually this matrix that gets multiplied first, which happens to be T1, then this matrix, which is T2. So let's work this out. If we multiply these out, what we end up with is a 0. So in this case, we get negative 1. Then this times this will give us a 0. This times this will give us 0. And finally, this times this gives us 1. That's our transformation of T1, then T2. So now let's do T2 times T1. Okay, it's just the opposite way around. So 0, 1, negative 1, 0 times by 0, 1, 1, 0. So in this case, what we end up with is we get 1, and then 0, and then 0, and then negative 1. So you notice that we get a different transformation matrix in this example depending on the order we multiply them by. And that would make sense in our example here. Okay, a rotation then a reflection would skew the results of my transformation even if I just look at it on a graph like this. Okay, so that's why sometimes the order matters, but sometimes the order doesn't, just based on the transformation. And this is how transformation matrices work.